Hey everyone, grade 4. Today our section 8, we repeat again our first section, linear programming formulation. Our first example about product mix problem. We have a firm manufacture two products, B1 and B2. The profit per unit of the two products is $50 and $60 respectively. So the profit for B1 is $50 and the profit for B2 is $60. Both of the products require processing in three machines. The following table indicates the available machine hours per week and the time required on each machine for 1 unit of B1 and B2. So we have three machines, 1 and 2 and 3, and two products, B1 and B2, and available time in machine hours per week. So the profit for B1 is $50 and B2 is $60. And available time for the first constraint is 300 and second constraint is 509 and the third constraint is 812. So what is the required to formulate this product mix problem in linear programming form? So our solution strategy consists of 5 steps. The first step, identifying decision variables. So let x1 represents the amounts manufactured of B1 and x2 represents the amounts manufactured of B2. So number one, again, identifying decision variables. So let x1 represent the amounts manufactured of product B1 and x2 represent the amounts manufactured of product B2. This is the first step. Second step, determine the objective function. Our objective function here is maximize the profit. Here, maximize the profit. So 50 x1 plus 60 x2. Again, so our objective function to maximize the unit profit, we need to get at least 50 x1 and 60 x2, the unit profit. Step 3, determine the constraint. We have three constraints. The first constraint for machine 1 is 2x1 plus x2 less than or equal 300 from table. So 2x1 plus x2 less than or equal 300. Why less than or equal? Because that is the available time for us. This is limited time for us. So we don't have much time to produce what we want. We have only 300 hours per week to manufacture B1 and B2. B1 needs at least 2 hours to manufacture 1 unit of it, and B2 needs 1 hour to produce one unit from B2. And the total available time for both products in machine 1, 300 hours per week. Second constraint for machine 2 will equal 3x1, the same, plus 4x2 less than or equal 509. So again, the second constraint for machine 2 will equal 3x1 plus 4x2 less than or equal 509. The third constraint for machine 3 will equal 4x1 plus 7x2 less than or equal 812. So again, the third constraint for machine 3 will equal 4x1 plus 7x2 less than or equal 812. Step 4, non-negativity constraint. We write this step 4 in all equations. So x1 and x2 decision variables should be greater than or equal 0. Last step, step 5, we write again all the previous. So maximize z 50x1 plus 60x2 subject to 2x1 plus x2 less than or equal 300. This is the first constraint. Second constraint, 3x1 plus 4x2 less than or equal 509. And third constraint, 4x1 plus 7x2 less than or equal 812. And non-negativity constraint, x1 and x2 greater than or equal 0. This is the complete mathematical model for this question. Example 2, we have three departments, Department A, Department B, and Department C. We have two products, tables and chairs, and the available capacity for each department. The available capacity for Department A is 1000 hours, and the available capacity for Department B is 1800. And last thing, Department C, the available time with 1400 hours. The selling price per unit for one table is 140, and one chair is $70, and the available cost per one table is $80, and one chair is $45. The required is formulated linear programming to maximize profit. So again, our solution strategy consists of 5 steps. The first step to identify the decision variables. So let x1 represent the quantity of tables will be produced, and x2 represent the quantity of chairs will be produced. This is the first step. Second step, determine the objective function. Our objective function here is to maximize profit. So the selling price per unit for table or x1 140, and a variable cost for table for one unit of table or one table is $80. So the contribution margin per unit equal 140 minus $80 equal $60. The same we do with a chair. The selling price per one chair is $70, and variable cost per one chair is equal 45. So the contribution margin equal 25. $70 minus 45 equal $25. When we our required is a linear model to maximize the profit, we focus on variable cost. We don't focus on fixed cost because fixed costs don't differentiate between alternatives. So we determine contribution margin per unit for each product to maximize it. So maximize 60x1 plus 25x2. This is our objective function. Step 3, determine constraints. The first constraint for department A will equal x1 plus 2x2 less than or equal 1000. So again, the constraint 1 for department A will equal 1x1 or x1 plus 2x2 less than or equal 1000. Second constraint for department B, 3x1 plus 4x2 less than or equal 1800. So again, 3x1 plus 4x2 less than or equal 1800. Constraint 3 for department C, 5x1 plus 3x2 less than or equal 1400. So the third constraint equal 5x1 plus 3x2 less than or equal 1400. And don't forget to write a non-negative constraint in all questions. X1 here are decision variables. X1 and X2 should be equal or greater than or equal 0. Step 5, last step, we write again the complete mathematical model. In our example, objective function was maximize z equal 60x1 plus 25x2 subject to three constraints. The first constraint x1 plus 2x2 less than or equal 1000. Second constraint 3x1 plus 4x2 less than or equal 1800. And third constraint 5x1 x1 plus 3x2 less than or equal 1400. And the non-negative constraint x1 x2 should greater than or equal 0.